Yeah. So basically, that's what we'll be doing today. And it's just today we plan to, I'll start by going through the slides. I'll share my screen. And the idea is just to, just do a brief walkthrough of, deep learning and, some neural networks. Then we can start, writing our codes. So I've taken this week section, and this training is brought to us by our Knowledge and Skills Forum. So I'll start by introduction. Then I would talk about deep learning, some of the motivations behind deep learning and the artificial neural networks, and some of the required skills, knowledge for computer vision. Well, yeah, it's not limited to computer vision actually. So it's also it's open to other applications like NLP. So sorry, I just use computer vision. And some of the applications and some challenges and complexity of neural networks. And so, as we all know, artificial intelligence has revolutionized, numerous industries from, engineering to production, to finance, technology. There are a lot. And also we should understand that machine learning is just a subset of artificial intelligence. So where system learns from data, identify patterns and make decisions. So already we introduced this last week, and we implemented some simple machine learning algorithms, for just simple problems. On the other hand, we have neural networks and deep learning. They are specialized subfields of machine learning, and it has been gaining momentum over the years due to its sophisticated kind of results, and with also increasing computational resources, deep learning has really surpassed some of well-known classical machine learning algorithms. Right? And so now we move to deep learning. So what is deep learning? As you can see, it's it's a broader family of machine learning methods, but it's based on artificial neural networks with representative learning. And so what it does, it allows machines to solve complex problems, even without, even when using a data set that is very diverse, unstructured, and interconnected. And it's capable of modeling complex patterns in data by using this backpropagation algorithm to adjust the weight and bias during training. So it allows the model to efficiently learn and represent the target. So basically, we also implemented this also in a kind of simple fashion last week. The forward pass, predict the results, then we do a back propagation. We do the weight and the bias update. And one of the major difference between machine learning and deep learning is we can see that the major difference is in the feature extraction. We see that in classical machine learning, features needs to be manually extracted from the raw data. And this process can require domain knowledge, right? And it may not always be easy, you understand, to extract the most relevant feature of a data. However, in deep learning, the feature extraction is done automatically by the model. So as you can see here, we have the feature extraction manually done, and we train the model to for the classification problem or any other problem we wish to solve. In deep learning, we just build this architecture, and the model learns to extract this feature automatically, right? And, another key difference is in, data dependency. So we have machine learning. So the deep learning actually, tends to perform better as the amount of data, increases. And whereas in classical machine learning, this algorithm tends to, reach a plateau. And when it gets to that point, the model doesn't improve, even with, increasing number of data, amount of data. And well, another major difference also could be in the computational resources requirements. Deep learning is highly computationally expensive. And these days you need to train your model on the GPU enabled machine, so as to run this model in parallel. You parallelize it, and you get results fast. And there are also, just also a few comparison between the classical machine learning, and deep learning. So the next thing is, what is artificial neural networks, and what is the motivation? So the basic, or how can I say, the artificial neural network is just motivated from biological neural networks, which is the brain nervous system. And think about the building blocks. The basic building blocks of a biological nervous systems are the neurons, right? And if we look at this image to the left, we see that each of these neurons they receive signals from a large number of other neurons through these dendrites, through this structure called dendrites, right? And if the signals that are received reach a certain threshold or something, then the neuron would fire, and it sends that signal down, to down, you can see down its axon to other neurons, that it's connected to. So basically, think about as human, or as human, we react to so many things, right? We have feelings, we have emotions, we have mood or something. So a lot of things. And you can think about the brain trying to interpret what we perceive, right? For example, you are happy and you are sad. I can imagine that there is a part of your brain that is interpreting what what you're feeling, right? Of course, if you're happy, the question is, how do you know you're happy? There is a portion of the brain that is responsible, or more or less that would fire, that would activate if you're actually in that happy mode. On the other hand, if one is sad or one is crying, something like that, then you should know that there is also different neurons that would also trigger that emotion or something like that. So it's also how this kind of artificial neural network works. To the right, you find kind of something, that a neural network that is created artificially. And think about this input, like what we did last week, or inputs are just these features, right? The features of our data points that we want to maybe predict. We want to do something. Already, you know what weights, what the weights are. So they are just the coefficients, right? So the coefficient of these input features, these features, right? And they give kind of the weights are particularly responsible for it's a kind of weighted value, and it gives preference. It gives preference to that particular feature. So what it means is, probably if I assign, if the model is training, after the model trains, and you find out that for this particular feature, the model assigns a larger weight, compared to others, then what it means is that that feature has to be very, very important in the model prediction. It's just like you want to you are giving, so you are kind of you want to interpret the relevance of these features by this weight, right? And that is what it means. And so what we didn't talk about last week was this kind of this layer. And already we know weight. We talked about that last week. We know input features, and we perform the linear operation, right? Remember, and where we multiply the weight by the input, then plus a bias. Now, in linear regression, remember the output is in like they are real numbers, real values. They are legit, and these values are between minus infinity and infinity. Of course, for linear regression or something, we don't have to convert the output, because we are working with continuous values. However, in problems like classification problems, where we are working with predicting classes, we want to work with probabilities, then yes, I mentioned that we convert this output to probabilities, that is between 0 and 1. That is in the case of we are strictly working with probabilities. However, here we are not sure if we are done with whatever we want to predict, and we can see this as a kind of the mechanism, something like we want to add something, just as we have defined here, when something for the biological neural networks, when the if the signal that is received exceed a threshold or something, then it's going to fire, just like how I explained how the feelings of happiness and sadness, the neurons, I'm sure the signals, the neurons that receive these signals would fire differently. And because in artificial neural networks, we don't, compared to the brain, this is just done automatically. But in artificial case, we have to artificially model this activation functions. So these functions are responsible for firing a neuron. They decide if a neuron is going to fire or not. And when we start the implementation, I would also show us what these activation functions can be. And this sum is just already what you know, because if you remember, when we're working with when we're working with when we wanted to predict y at the last time, what do? We take the first weight, multiply it by the first feature, second weight, and the second feature, right? And ... So that is just basically taking the sum of of this dot product, right? And that is what you see here. This is just the sum. And the result, because this is not the final prediction, let's call it Z, just as we did in case of logistic regression. Then this Z will feed this Z into this activation function. And this activation function will decide if this Z would fire or not. That is just basically what it's doing. And yeah, so now for deep neural, so what are actually deep neural networks? So the word deep comes from, already we have talked about yeah. So when we talk about multiple hidden layers, like if you look at this kind of layers now, this kind of network, we find this to be a shallow neural network, right? Because it's just one hidden neural network. We have one hidden layer rather. So, and how do we interpret this? So first, let me interpret this. So remember the last time, so let me go to the previous slide. When we had this is just, just think about this as what I've explained. You have the weight and you sum, and we only have one neuron here, just one neuron, right? In the case of simple linear regression or or linear regression, or logistic problem, logistic regression, we find out that this whole thing is just what we tend to have at the output. But in the case of neural network, we don't just want one neuron. We don't want one result here that would decide the model prediction. So we want to add more like neurons. And this is basically what you see here. So if I remove all of this, we are just, in this other scenario. But as you can see, we have more neurons. So these neurons are now acting like kind of, so it's, the neurons are acting like kind of, mechanisms that, that would be responsible for, doing these complex operations, right? And, these neurons are responsible for a lot of things. So one could be responsible for probably extracting the shape. If we're working with images, extracting the shapes, or let's say the edges rather. And maybe this might be responsible for, for the other, more complex features, then on and on. So when we talk about deep, it refers to multiple hidden layers. So what you have here, the layers between the input and the output is what they call the hidden layer, because it's hidden, right? It's hidden. And as you can see here, we have one hidden layer. Here we have 1, 2, 3, 4. We have 4 hidden layers. And so these hidden layers here helps, to perform kind of complex operations on massive amount of structured and unstructured data. So what this would do is, it tries to, as you can see, the network, it's connected in a way that information is passed from one layer to the other, trying to extract this, features that is responsible for the model prediction. And yeah, so the word deep learning comes from the fact that, if you have networks with multiple hidden layers, then the term deep comes because it's deep, unlike this that is quite shallow. So it's just one, just not deep, just one. And, the deeper the network, then the more likely, you have more complex operation. In particular, if you have problems that are quite complex, then the deep neural networks can be very helpful. However, deep neural network doesn't guarantee that your model would perform best, because also it might lead to overfitting, because the activation functions in each of these neurons adds this kind of non-linearity. And of course, we don't want to overfit, right? But there are also regularization methods that can handle this, and which we would also talk about tomorrow. Now, so like I said, we have the component of neural networks. And if you see, the components here are just the building blocks of the neural networks I've explained. We have the neurons. The neurons are just those circles that you see. And why it is like that is because these neurons are responsible for, interpreting, the mechanisms of, feature extraction until model prediction, right? So what you see here is nothing more than that. It's just a linear operation. You just take the linear operation, and the result would be, we will feed the output result into the activation function, right? Because we are not done yet. So we feed it into the activation function, then the results here, we pass it over to the next, layer. It performs also the same, operation, linear operation, that is the weight times, right, plus bias, then, and on until we get to this output layer. So that's just it. And the weight also, we've talked about that. Okay, the neurons are just, it receives the input and generate an output, right? Yeah, so based on the activation function. Then the weights are the coefficients. It transforms the input data within the network layers. And we have the bias time, which is just the intersect. It's an additional parameter that helps the model to be more flexible. And we have the activation functions. It decides whether a neuron should be activated or not. They help to add non-linearity to the network. And, the result from one input from the output would be mapped to values between 0 and 1 or -1 and 1. And that value, well, this is in the case of probably if you're thinking about, this doesn't necessarily have to be 0 and 1, right? Yeah, this might just be maybe at the end of the model prediction, but also this is quite different. This also is a kind of like the tan-ish activation function. It maps the output between -1 and 1. However, in most like images or other applications, we would have activation functions like ReLU. We'll talk about that. I would explain that in details. Now, what does artificial neural network looks like? So this is what we are trying to predict. So this is a network architecture, and we are trying to here is the input, and you see we feed in this image 7 to this input. So what we do here is we flatten the image, and after flattening the image, we just, and these are the hidden layers, as you can see. So we have different nodes, that we perform this linear operation. We pass it through also an activation function, and then it moves to the second layer. And by doing that, the model begins to learn more complex patterns, right? And until it gets to this output. And what you see here is we're trying to predict handwritten digits between 0 and 9, and you see that the model would output kind of probability distribute. So at the end of the day, we expect our model to output probability distribution, and with this result, we can decide what the model predicts. For example, we see that the highest probability is assigned to number 7, so which means that the model does well at identifying these handwritten digits. Tomorrow we will be implementing this. So this will be the project we'll be implementing, and we will do live project of the model can, when we feed in an image of an image and a handwritten digit image into the model, it would output these numbers. Yeah. And you can see the input neuron is 784 because we flattened this 28 by 28. Because an image is like kind of two, in this case, two-dimensional grid. It's a grid, 2D. And for this kind of architecture, we cannot feed in an image of 2D into this just one stacked neurons like this. So what we can do is we flatten it 28 by 28. We have 784. That is, we flatten it by the rows. We just pick one row, we pick the second row, we stack it by the so we line it something like this, right? So let me explain in terms of. So let me explain. So this is one handwritten digit. This is 8, and this is what 8 would look like if you if you try to read it if you try to read it. This is how the computer interprets or view an image. An image is just a bunch of pixel numbers representing the intensity of the image at that particular point. So as you can see, this is a black and white image. The black is represented by 0, and typically the white is represented by 255. This is an 8-bit image. And as you can see, if you notice these regions where we have this 8, we have this, we have values assigned to them. And these values just gives the intensity, right? If the image is all black, that is, if there is nothing here, we just have zeros everywhere. That is just black image. So how do we feed in this kind of image into this architecture? For example, if this image is 28, that is 28 by rows, and 28 by rows, and 28 by columns. What we'll do is we take this first row. Let's say this is 24. We line it up like this, right? We pick the second row. we line it up. So we keep, we keep stacking them together, and you get 784, just one long vector. That is, these numbers already stacked together. So just saying, so that you would understand that, okay, when you have an image, you have to flatten it if you want to, feed it into this kind of architecture. On the other hand, there is also what we call a convolutional neural network. It's different from the RNN I showed you, because now we work directly with image. So we are not going to flatten it. We will just, compared to this, where we have just neurons, we have different neurons. I mean, we have different weight on top of these flattened pixel values. So, and we have these weights, that performs this linear operation and, activation function and things like this. In this kind of scenario, we don't work with, just a kind of one, we don't work with this. So we don't work with this kind of, neuron, this, one row or kind of one, column, neurons, something like that. But we work with, we work with a kind of, we work with filters. So this what you see here, they are just filters. So this just, in a way, represent those circles you see in this, in these scenarios. Because here we are just working with pixel, just one pixel, each pixel value, so we can easily map these weights to, to each neurons, as you can see, and we perform the operation. For this, we use a filter kernel. So as you can see, it's also like, it's a two-dimensional matrix. So it's a matrix of weight, right? In the other one, it's the weight is not in for each pixel is not a matrix. It's just one number. But here, because we are working with grid, like 2D image, we work with filters. So they're also called kernels. So they are just metrics of weight. And what we do is we slide it across, this image. We slide it in a way, so we stride it over the input image, and we perform dot product. So, for example, if this image is, let's say, 28 by 28, and this kernel is 3 by 3, we map this 3 by 3 kernel to the first 3 by 3 pixel values here, and we perform element-wise product, right? And each of these kernels has its own bias, just like as we have in the other one, that each of the neurons would have its own bias. And typically in the CNN, it's very useful for images, because images are in 2Ds, or also we have it could also be videos, could be also in 3Ds and 3D. So when we perform this this operation, so we call it so the result, the transformed version of the image with this feature map is what with these kernels is what we call feature maps, or the convolved features. And then it passed through this kind of max pool, because also we want to extract the most important feature of the image. Of course, in images are, we might not, some part of, so in max pool just reduce the spatial dimension of an image. And, it takes the maximum of, of each of these corresponding feature maps, right? For example, if the feature map is like, if we have, for each of the, let's say 3 by, because if we stride this feature map across this image, then we just want to take the maximum of, depends on, the kind of kernel you define. If it's 3 by 3, it comes here, take the first 3 by 3, then it extracts the maximum value. And then that is what we talk about max pool. So it's a pooling operation, and it takes the maximum. And then, it goes through kind of fully connected layers where everything is, the whole feature extraction has been done, combined, and then the, the classification is done here. And, it outputs a dog or a cat, just like probability distribution. So we would also apply this, we would apply both methods to the digit classification tomorrow. So that will be the project. And so when we talk about feature extraction, so think about this image as the raw data, and think about, maybe the first, because here, of course, we won't only have just one layer of this, right? And in CNN, we call this one conv layer, because just as we have here, this one is one layer. In CNN, this would be regarded as just one layer. We have the feature, the convert feature plus the max pooling event, the max pooling, and any other thing you want to perform. It's called the one conv layer. But we might have more conv layer, right? Because imagine we want to classify cat and dogs. We want the model to, to do high level feature extraction, right? And this is what we mean when we talk about, feature extraction. So first of all, think about the first conv layer responsible for, just taking the edges, right? The edges, the shapes, or somewhere, maybe the edges, or just, think about just probably the rough edges, not much in detail. That is the low level feature. And the mid-level feature, now think about, this layer is responsible for, picking the eyebrows, the nose. In the case of cat and dog, you can imagine, think about cat and dog, picking their faces, the structure of the nose, because a cat and a dog, I think they have different, so these are kind of mid-level. And the high level is, it goes even deeper, tries to now combine all of these, features from low level to mid, try to combine them now to see that, okay, what is so peculiar about this, cat or dogs or humans or whatever. And then, it's able to to tell, that, okay, this belongs to this actually, and this belongs to this. So this is basically what we talk about, the steps, and this is just done automatically. We don't have to do this manually, right? Okay, and the question is CNN better than ANN? Like I've explained, CNN are very applicable in in problem. When we are working with images, right? And it's very important to know that it's specifically designed for for such kind of data, like images, most especially images or frames, like video frames or something. On the other hand, we have ANN to be very vast. It's applied to quite a lot of problems, but specifically CNN is mostly specific to grid-like data like images. So usually you would have better results when you use CNN on images. However, we can also use ANN on images. Like I said, we can flatten the image and we can use the simple ANN. But the question is, if the image is very complex and if the problem you are trying to solve is very complex, then ANN might not actually capture all of these high-level feature, right? And in this case, CNN is better. So always know when to use which. Tomorrow we would also apply both on this handwritten digit so we can see the performance. Okay, now to be very fast because of time, so we have the recurrent neural network. So RNN is just like, what the only difference is the recurrent here. There are also types of artificial neural networks that are designed to recognize patterns in sequence, and sequence of data, like test genomes, like, time series data, right? And you see one data point is just sequence. And, think about the time series data of maybe 1 year. So you have data values of 1 year. That would just be one data point. You have another one of another year, and you see that it's recurrent. We cannot predict the beginning. We cannot predict the end from the beginning. We have to go in sequence because it's in sequence, right? It's something like kind of in series. So we have to move from one step to the other, and as you can see, move from one to the other. Then at each point, it predicts it predicts the it does a prediction for the next time step. Here it does another prediction, right? Until the last point at t. So think about 1 to t as the time. In terms of time series data, then in terms of test, it's just like, from the beginning of one. So if you have a sentence, think about a sentence. So for example, RNN has the ability to process. So think about this as a sentence in an RNN. This would be at time equals 1. If you are working at word level, word, not character, word. So RNN can be the first. You want to take this, predict the next word as, take this, predict the next word D, right? And that is what we are talking about. But for the purpose of this training, we'll be looking at computer vision, right? Because that was the main purpose. Our project would be on computer vision, just simple computer vision. But along the line, we can think about also taking we can just think about taking a training on that's more specialized. So this is not limited to computer vision, like I said. I'm sorry that I just included computer vision. Generally, you have to understand calculus, because like what we did last week, the idea of finding the derivatives, you want to back propagate. We want to know how much we nudge, when we nudge a particular parameter, how does it affect when we nudge a weight, how can we update so we want to know how much the model prediction can get better when we nudge a weight. And that is the idea, the whole idea of gradient descent. You have your model, we predict something, and we want to do this feedback loop. We want to nudge this parameter. So if we nudge it, can it do better? Something like that, because so what decides that would be, how much loss we would have between the predicted value and the original value, right? In case of a supervised learning problem. We have linear algebra because we also work with metrics, right? We have probability and statistics, very important. We work with also probability distribution. We also have signal processing. This also, it doesn't have to be in-depth, but just understand how neural network moves. Like, just think about this. So across the network, think about, think about it as a flow of information. So there are signals that are passing through. And, we want to know if I receive this signal, what would fire, in terms of, just kind of low level idea. But of course, we know there are a lot of physics. We also have projective geometry, computational geometry. We have optimization theory. Most of the problems we do, the optimization problems. We also have control theory. We want to know how, we want to understand the complete dynamics, of our problems. This is not, it's not limited to all of this. There are also more things to know, but I would advise you to just start from, from what you have to know. Depending on the kind of problems you want to solve. And we also have softwares and programs, programming languages for, not limited to computer vision, but just generally, even though you want to work with, you want to work in areas of natural language processing, and also, and also finance, anything, robotics, think about anything. We have language like Python, C++, R, Julia, MATLAB. Well, in the area of machine learning, Python is more dominant because, we have lots of libraries, very sophisticated libraries. And the frameworks like TensorFlow, PyTorch, NumPy, sklearn, SkyImage. We have OpenCV, for computer vision problems. We also have, for today, we'll be using PyTorch, right? Yes. And we have, web-based softwares you can use to deploy your models, Django, we also have fast APIs, we have Node.js, we have JavaScript. We also have cloud-based platforms like Amazon, SageMaker, Google Cloud. We have Azure, Microsoft, and you can read about them, right? And at the end of the day, you want to build models, you want to, from development to production, and this you have to consider. We also have the mobile-based softwares like TensorFlow Lite. So if you are if you are much interested with mobile applications, unlike web, you can also think about, frameworks. We also have containers like Docker. We also have Kubeflow, and etc. So you can also read about, these tools that you can use from development stage, from developing your model down to production. Okay, the applications, we have lots of applications in image recognition, we have natural language processing, we have in time series prediction, we have reinforcement learning, we also have generative models. And I'll give some examples. So here we have object detection. The model can detect objects and it can, identify and label these objects, as you can see. These are just, boxes. They are bounding boxes. When the model predicts, it's able to, wrap this box around this object. We also have segmentation. So you can see the model is able to segment this car, as you can see. Also this bus, it's, you can see. And these trees, the trees here is segmented with this green color. The sky is segmented in this blue. The house segmented with this yellow. Well, this is just a general form of segmentation. You can even go ahead to say, okay, I want to segment this car, the tires, the glasses, right? The screens and things like that. Depends on you. But for this problem, it's just all red, probably at a high level segmentation. We also have face recognition. You can build models that can identify, your face. We also have cool application in medical imaging, right? You can use it for, for medical diagnosis. You can use it to, generate data, medical images. You can also use it for reconstructions or things like that. Also in language translation, as you can see, Google Translate. You can move from one language to the other. This is basically the problem. This is NLP, and yeah, very interesting. We also have time series prediction, which is we want to predict, probably stock price. As you can see, the true price is in blue, and the orange is the predicted value. Also, in industrial robots, we can also build. Some of these sophisticated models can also be applied in industries like automobile or production, where you build robots that can actually perform tasks based on, you have trained this based on this, some of these sophisticated algorithms. And also you have text generation. You must have heard about ChatGPT, generative pre-trained transformer. And what it can do is, it learns, it uses this transformer architecture to, learn high level, probably character or word level language models. And you can actually ask questions and it can provide you with answers. And, everything just boils down on, training model that can solve problems. And also we have an area of generative deep learning called generative models. So where you can actually generate fake images, right? And so these images you find here, they don't exist. So what they have done is that they have trained faces, people, and they have trained the model in such a way that the model can, generate image, real faces. However, these faces you see, they are completely unique. They don't exist in the training data. So what the model has done is the model has been able to learn how to build human face, like the ear, the eyes, the nose, the mouth, And think about it, also the same it's the same it's the same procedure for text generation platforms like ChatGPT, right? Because what you do is that you ask a question and it generates something. It just generates this text. If I ask ChatGPT this same question, it's not going to give me this answer again. It's going to give me something else. So you can see the model has learned. So also this, it has learned to generate faces of people. And these people don't exist. Yeah, it sounds weird, but they don't exist. Yeah, so this is one of the cool applications of, deep learning. Also quite advanced, neural networks like transformers and things like that. You will get there when probably you are more interested in more advanced application and many more. And some of the challenges is that, you require large amount of data. Like I said, there is this high, data dependency, right? You need a lot of data. And the more data you have, the more relevant data you have, the better your model performance. And it's computationally expensive, right? Because I also mentioned that you need computational resources. There's also a problem of overfitting because most times when your network is deep, this non-linearity thing begins to, make your model overfit. And then you have to think about how to, checkmate this. There are ways to, to actually to regularize your model such that, it doesn't overfit. And we have local minimum in optimization. So because it's really in high dimension, there's always a problem of, your optimization problem where during gradient descent, your model is stuck. It's stuck at a local minimum, right? Because you don't want it to be stuck at the kind of, local minimum. You want it to be, you want it to go down because, this just translates to the loss. You want to decrease the loss. You want it to settle at the global minimum, not at some, think about it like a hill or something. And you see in a hill, or let's say in a rough surface, you see there are places where you just settle down, but it's not the global minimum. That is, you can still go further down. Just think about someone going for hiking, starts from the top and wants to go to the lowest part of that hill, right? And it's also a problem. And there are also optimization technique to solve that. And yeah, these are called the optimization frameworks that we can use to add momentum to this, that can push this this loss down to its global minimum. And there's difficulty in understanding and interpreting neural networks because it's often referred to as black box. Because if you think about the hidden layer, it's just some kind of complex operations going on there. We don't even know. We cannot really interpret. We don't understand. Well, even though we can kind of give a rough interpretation, but it's still not completely clear how these complex interactions is able to perform quite well. And there's a challenge of choosing the right architecture, hyperparameters. There are things, hyperparameters are flexible parameters you can change, you can tune. And the problem is which is the best, which is not the best. So probably if you can understand that these challenges, then it makes sense that you can build your model ensuring that you are not stuck in one of these challenges. And the goal is to ensure that your model is able to do something nice and you can interpret your result. Okay, let's go to yes, sorry. So yeah, we'll just be just at the same time, I'll be talking about PyTorch. PyTorch, as you can see, it's an open source machine learning library that is based on it's a machine learning library that is based on the Torch library. So PyTorch is from Facebook, and you also have TensorFlow from Google. From Google. So for me, I started using TensorFlow. Along the line, I found PyTorch more Pythonic, so I switched to PyTorch. But regardless, you can stick to whatever framework. Just understand how it works generally. And so what are tensors? So think about tensors as just a kind of their data structure, used in linear algebra. They are like vectors and matrices, and you want to think about them as a kind of generalized multi-dimensional arrays, right? And yeah, I think I didn't explicitly talk about arrays, but they're just, when we talk about dimensional arrays, we just talk about like just matrix vectors, like 1D tensor. You can just say 1D array, which is just an array of numbers. But tensor is just a more generalized way of representing a multi-dimensional array. So you can a two-dimensional array is just also a two-dimensional tensor. So it doesn't matter. It's just a more generalized way. Yeah. So we have, of course, we have tensors could have in different dimensions. We have 0 dimension. That is, a tensor of order 0 is just a scalar. It's just a number because it has no dimension. It's just a scalar. You cannot access this number with some kind of indexing. It's just no dimension. I would explain that also. We have 1 dimension. It's just a 1D tensor. It's just an array of numbers. And you can often call the vector here. And you can it's just in 1 dimension. It's just like you stack up, you line up numbers as vectors, and you can, if you want to index into any of these vector, then you can use the index. You can index into any of the numbers in the vector. 2D, of course, matrix, because now we're talking about 2 dimension. Matrix is rows and columns, right? And you need to index for an item in the matrix. Then you have 3D and higher, right? And it could be more 4D, 5D. So 3D is just like a cube, right? You have the like length, breadth, then kind of like depth or height or something. So think about 3D like this. You have the length, breadth, and height. Length, breadth, and height. Yeah. So, and you have 4D, 4 dimensions. So what you have is 4D now. We take 3Ds, then stacked, right? And as you can see, this is a 4D tensor because you also have, by the rows, you have the rows, and the columns themselves are 3D tensors. So in this case, you can have 1, 2, 3, 4, 5, 6, 7. You can have 7 by whatever, by this 3D tensor. You have 5D, you have 6D, and yeah, and so on. So now, what is the key difference between NumPy array and PyTorch? So particularly, PyTorch is is designed for GPU. And if you think about GPU, they are just graphics processing units, and they help to accelerate computations. So in parallel, kind of parallelized manner. And especially when you're working with deep neural networks, because it's really deep, you have lots of parameters, like it could be up to millions. Your CPU cannot handle this. I mean, it can, but it might take forever to even get just very simple results. So you would need the GPU. But the good thing is that the Google Colab offers us this GPU. And if you come here, if you come to your runtime, you would see it. Just come here, and you can change your runtime. And here is still, there is nothing. So if you want to change to GPU, then you can change to GPU. So if you switch to GPU, you have this graphics processing thing enabled on your notebook, and you can run even, you can run deeper networks, and you can use it to solve complex problems. And it has also deep learning support. It's particularly designed for this kind of neural networks things, functions, the back propagations, and things like that. So because in previous implementation where we use simple NumPy, you notice that we had to calculate the loss. We had to implement the loss ourselves during the back propagation. I still have the code here. We'll show that. But in PyTorch or in frameworks like this, you don't have to, you don't have to calculate this. There are already inbuilt methods that helps to calculate this, right? So you don't have to. And there are also lots of, key differences. Tensor operations, right? There are also a lot of operations in tensors that you won't find in NumPy. And there is this dynamic computation graph because if you think about the neural network as a kind of graph, so it keeps track of this, it's very dynamic, such that the graph, so when you carry out an operation, there's an abstract graph that that is stored somewhere. It keeps track, and it changes on the fly at once during the iteration, and it can help to a lot during back propagation, forward, backward, right? And we would also see that when we start to write the code. And I mean, this is just something very basic, right? There are more, and I would advise you to also read more about Torch, PyTorch. But let's start. Of course, we have to import Torch, which is the first thing we have to do. Yeah. And let us create a 0D tensor, like we talked about. A 0D tensor is just a scalar.
Can you hear me?
And, when we import the Torch, you just call the tensor. So we want to create a 0D tensor of 7, number 7. When you run this, you have this, right? So it's a tensor. If you check the shape, and the shape here gives you the, right? Because you want to know the shape. You want to know in like the dimension. It's just blank because, like I said, a scalar has no dimension. And the data type is torch.int64. Remember, we taught this, so it has this 64, how the number is stored in bits, right? And it's an integer, 64-bit. So yeah, that's just basically for scalars, very easy. You call the torch tensor. You can specify the data type if you like. You can specify if you want a float, but by default, this tensor outputs integer of 64. But probably if you want float or something, there is also, you can specify, right? And you can specify if you want it to be a float. Remember, floats are just, how can I say, floats are like decimals, right? You can see it has changed to torch float 32. And if you notice, there is now a point because, float represents, decimal point. But by default is int 64, right? So if you don't specify anything, and if I run it now, this point would go because integers, of course, integers they don't have decimals, right? So you see. So if you want to define your tensor, you know what to do. And now let's quickly create a 1D tensor. What we just do now is that instead of putting just one number, we put in, a list of numbers. Then we wrap it around this, square bracket. So this, it adds one dimension. And you can see now the dimension is now, the shape is just 5. So it's a row vector, right? It's a row vector, as you can see. I mean, it depends on how you translate it. You can decide to say, okay, you want to translate it to be a column vector, then you take the transpose, but it's a row vector, right? And as you can see, 1, 2, 3, 4, 5, integer 64. Here you can also, like, because the dir method just gives also attributes of, there are a lot of things you can find in Torch, a lot. As you can see, what we have been using, like, for example, so if you want to know more, you really have to read, all the attributes, like this tensor we have been using is here. So Torch is just see it as a kind of the class method holding all of these attributes, then tensor is just, a method in the class there. Okay, now let's go to 2-dimension, right? So we want to create a 2-dimensional tensor. And so what we can do now is that instead of just creating a list of numbers, right here, we can just, add more. You can add more we can add more lists separated by commas, and we'll wrap them also in one. We wrap all of these lists also in another list, and we get this two-dimensional. As you can see now, if you print the shape, we'll have 3 by 3. So, and each of these points here can be indexed using 2 values. So now if I want to, you see the values? You see these values here? If I want to access, let's say this 0.5 or, okay, it's the same number. Yeah. I mean, but if you want to access this, it's in the first row and second column. Second column. So probably you can just, you can print to, you can access it like this. So you specify the row, the first row and the second column. When you print this, you get 0.5. So which is this. And because why you have to represent, you have to use 2 index because it's 2-dimensional. That is one by the row and the other by the column. In this case, because it's 1 dimension, we can only index it using 1 number, right? And so we just specify, let's say you want to get the 3rd index, as you can see, 4. Because Python index starts from 0, 1, 2, 3, get the 4, right? Yeah, so yeah, it's just like how list works. So now let's create a 3D tensor. We've created a 2D tensor. Let's create a 3D tensor. So what we can do is, we can think about, creating a yellow, like a colored image, just an image with 3 color channel: red, green, blue. And you see here, you have 2500. As you can see, red, the first entry here stands for red, green, blue. And here I've defined the first red here. The second, along the first row, define green. And now I move to the second row, I define blue. And the third, I define white. So when you run this, you get, you see, it's just, 3 color. You see the dimension, 2 by 2 by 2 by 2 by 3. So we have we have this here, 2 by 3. We have 2 by 3, right? And we also have this 2 here to represent, like just stacked. We have, 2 stacked 2 by 2, image by rows. So this is how you create tensors. Yeah, nothing much. You just have to know, when you specify, a square braces, you introduce a new dimension, right? Okay, now let's proceed. Now let's, yeah, we can convert, grayscale. We can convert this colored image to grayscale. Yes. And well, there is a way to do that. We can also apply formula. There is this formula. If you have a colored image, there are some image, sometimes with your phone, if you apply filters, you can convert your image to black and white. So this is just what is going on. So they multiply the red channels, that is the pixels along the red channels, they multiply it with this value. The pixels along the green channel, because colored image have this, red RGB, red, green, blue, and the green multiplied by this and the blue. And if I pick this image that I've just created now, as you can see, tensor 3D here, if I convert it now to black and white, I get this. As you can see, I've converted it to black and white. So the blue, everything is now black and white. Yes, so that's just by the way. And we can also create tensors by just, we can convert a NumPy array to tensor. This is a simple NumPy array. As you can see, we created a 2 by 2 NumPy. And, the question is, now here we want to multiply, say here we created a 2 by 2 NumPy, which is this NP image. And here I've created a tensor image, also 2 by 2, the same, just exactly. But now I want to multiply this tensor with NumPy. It's going to throw an error. as you can see, it will throw error here, and it will complain that unsupported operand types for NumPy, ND array, and tensor. You cannot multiply a NumPy array with a tensor. So they are both different. So what you have to do is that we can convert this NumPy that we created here to tensor, then we can carry out the operation. So how to do that? Because already we have created, this is the NumPy array we created here. And what we can do is, there is also a package in Torch that says from NumPy, that is, we can convert a NumPy array to tensor, to Torch tensor. And if you look at this, where I printed this whole thing, you will find it there. It has to be there. So you can look at these things and try to see, as you can see here from NumPy, there's also, as you can see, from file, there is from NumPy, there is from buffer. There are a lot of, functionalities of Torch. I would advise you to, you can start from, just one and try to understand all of these methods. Okay, so immediately when we convert when we convert that tensor NumPy to tensor, we just call torch.from NumPy. So it's telling Torch, this is a NumPy array. I want you to convert it to Torch from NumPy. And now we can now multiply. So you can see this is the this is the converted NumPy to tensor, and the tensor image, which we define here. Now the operation is possible because we have converted this NumPy array to tensor. You can only multiply a tensor by tensor. You cannot multiply a tensor by any other data type, like a tensor and an integer. It won't work. It has to be a tensor integer. So operations in PyTorch, just like as we have in NumPy, we can also add, like add. Like I said, I won't also say much, but there is here, you would see all of this. There is also add, if you look closely. So, okay, I think it's towards this side. Yeah, anything we do, you would find here. You can see add here. So as you can see, we can sum two tensors together. And here you can see we have a tensor. Of course, this is just a one-dimensional tensor. Of course, it's just like 1 by 1, something like that. So, this is just, a scalar rather. Then we have also another scalar 5. We want to sum 2 and 5. You just use the add, right? And you get 7. Mind you, it has to be a tensor also. Also for subtract, we want to subtract 5 from 2. So you use the sub, which stands for subtract, and you get -3. And you have the multiplication. You want to multiply mul, right? 2 times 5, 10. You have the division, torch.div. You have 2 divided by 5. And what you see here, any number you put here would be, so if it's division, A would be at the numerator. If it's multiplication, A will still be the first. If it's subtraction, as you can see, 2 minus 5. So be very careful. If you want to say 5 minus 2, then B has to come first before A. And if you run, you get 3. So now, basically, let's just jump in because we have just done a brief recap on module pipelines. So let's talk about module pipelines in general. We talked about that previous times, and we do the forward pass, and we do a backward pass, which is just the weight update. That is just basically what we are doing. And what do we mean by that? So now there's what we call autograd backprop optimization. So we just briefly talk about that. So now what I just did here was to define 2 tensor. Already we know how to define tensor, 2, right? 3. Now I added this required grad. Now what this means is that you can set it to be true if you want to track a computation. And what this required grad means is that we have imposed a kind of gradient update. Think about it as our weight in previous, examples. The weights are updated from, by doing this gradient. right? When we have the loss, we take the gradient of this loss with respect to this weight, right? And we update this weight using that update formula, right? And what we are saying is that we want to create a tensor that the weight, that the tensor can be updated. It's as simple as that. So in this scenario, we are not defining weight. I just want to explain to you what we talk, when we talk about, gradient, this is just basically what it means. So when you set this, PyTorch will begin to track that particular scalar, or weight. Yeah. Or anything. It doesn't have to be weight. If you just feel like, this weight, the value has to be updated somehow via some operations, then you have to put the required. By default, it is false. By default, it is false. And, when you run this, so, here I just define x1, x2, and here I perform an operation, y hat equals x1 plus x2. So here I'm just, I just define, some kind of operation, y hat equals s1 times x2. Nothing more. So in this case, our y hat just means our prediction. I'm just trying to show an illustration, right? And now I want to show the graph. Now, so this is basically what PyTorch would do, because I set this gradient to be true. Now, PyTorch will keep track of this. As you can see in the computational graph, you can see that this value, this x1, there is a gradient that it's expecting a kind of gradient update. So it has accumulated, some kind of it has accumulated. So it's expecting a grad update. Yeah, something like that. Okay, so what does it mean? So if I print x1, let's print x1. Let's print x1. Then you see what it's going to say. Now, you see it says require grad equal to true. So what it's saying is that, it's expecting from this accumulate grad, it's expecting that if we do a backward pass, if you look at this graph, you see the arrow pointing. What it means is that it is expecting a gradient. So it has to update this x1 via some, gradient calculation, something like that. What happens if I set this to false? Now, when you set it to false, now look at the computational graph. It has changed. The x1 has disappeared. And this is why PyTorch, or, these frameworks are very powerful, because I set this grad to false. PyTorch doesn't recognize it. So, and typically when you train your model, the idea is to train your model and to update the weight, right? So by default, when you instantiate a model, the weight, the required grad has to be true. So when I set it back to true, so now when it was false, PyTorch only just recognized this x2. Okay, now let's proceed. Okay, I didn't change it back to true. Okay, now it's now you can see. So now what is this? Mol backward. Now I need to talk about this. So when we perform this operation, y hat equals x1 plus x2, PyTorch says, okay, there is a multiplication has happened between x1 and x2. And as you can see the arrow, both arrows are pointing to more. So this mol means multiplication. So it's expecting a gradient that is based on this operation, right? As you can see, mol backward, and it outputs the y hat. So it's going to calculate this y hat with so if you find the gradient of y hat with respect to x1 and y hat with respect to x2, it is going to start, because this y hat is as a result of this product. So, and when you take when you kind of maybe when you are at this point, you want to take the y hat with respect to one of these two gradient because of this multiplication. Yes, and now let's go into just a brief explanation. So we are familiar with this method. This is mean square error. We talked about that also. And we have predicted our y-hat, I mean, just as an example. And so what we want to do is, how do we, update this x1 and x2? In this case, they're like the weight. We are not working with any input here. We are just doing some, random examples. So now remember, this is like our model. Think about this as our model. We have our y-hat, which is the prediction of the model, x1, x2, x1 times x2. And we want to do, a gradient. We want to get the loss. Remember, so now I'm assuming that my y, the true value is 4. That is what I would expect. Although our model predicts, let us print y-hat here. So our model predicts 6, as you can see. So that is the prediction. But we are expecting, y-hat. We are expecting our real value to be 4. Although it is 6 in reality, because we know that 2 times 3 is 6, but because we are just trying to simulate a kind of scenario where we have our output and we want to check if it differs from the output. So now we will take this y, that is the ground truth, from this formula, if you remember. We will subtract the the predicted model from, the predicted result from it, as you can see here, y-hat. And we take the square, which is the sum of square error. And now we have the loss, right? Now, remember the last time when we for the gradient of this for the gradient with respect to the parameters, remember, we calculated it by hand, right? I think I still have it here, but I don't want to show it yet. So we calculated it by hand. If you check the code, you would see the gradient with respect to the weight, rather, like the beta 1, I think, and the beta naught. Yeah. PyTorch can just do that for us, loss.backward, straight. We don't have to, write it by hand or something. And then once it performs this, we now want to check what is the gradient, what is the computed gradient, what is the computed gradient. Now, what it says that the computed gradient is 12 and the computed gradient is 8. And I'm going to explain. I have to explain this. Now, what does this mean? Now, remember when we perform this operation, y-hat equals x1 times x2. Now, I want us to to think about something. So now what this loss.backward is going to do is that from this loss, it is going to compute the gradient down to this x1, x2. And you know that our loss equals what? Y minus y-hat, right? And if you followed closely the class of last week, if you want to calculate the the gradient with respect to weight, you will use this kind of chain rule, right? So what it means is that we want to calculate the loss function with respect to, right, x1, like our simple calculus. And what it means is that we have to do first the L dy hat, remember, times the y hat over the x1. And this is a chain rule because we know that the loss is, is a function of, okay, sorry, this is supposed to be square because we squared it, remember? Okay, let me just, yeah. So this is the square of, the error, and we have the y-hat. So we have to take this with respect to y-hat, and then we take y-hat with respect to x1. So let us do same for, because we have 2 values. In this case, we have 2 weights, and this is what you get. So how did PyTorch arrive at this 12 and 8? How? Now, let's start. What is dl dy hat? So our simple calculus, if you want, let's start with this. So this is just, so let's start with this. So if we differentiate this with respect to y hat, we would have 2 times minus 1 times y minus y hat. Right? I hope I'm correct. Yeah, so it's just simple, you know, oh, okay, so I can zoom further. Okay, sorry for that. Yeah, I just saw the message now. So I've zoomed further. So now I'm still here. So remember, I want to show us why, you know, PyTorch I've just done this, you know, gradient thing, and we don't have to, you know, write it by hand. So our final, okay, yeah, this is for, sorry, I bring it down. Yeah, quickly, I'm going to be fast with this. So I'm still trying to calculate this. So you know, we have differentiated this loss with respect to y hat. If you know your calculus where you bring down the power, you know, you differentiate this with respect to y hat, that is -1, then, you know, you write and take 1 from this. Times, now what is dy at dx1? You know, this is your dy at dx1. Already, you know, if you differentiate dy at dx1, you know already it's just x2, right? Because your x1 here is just like, your x2 here is like a constant, right? So you just have x2, right? And that's just basically it. Now, so let's just, you know, so here we have -2 times, because this -1 times 2 equals 2. And we have, okay, let's just bring the x2 from here. Let's just join it to this place. And we have 2 times 2x2 times, you know, y minus y hat. Now, what would this give us? We have -2 times, what is x2? Remember, we define x2 to be 3 times, what is y minus y hat? Our y is 4 here, you see. And our y hat, which is the model prediction, is what? 6. Remember our y hat. So I'm just assuming. So what do we have? We have -6 times -2, and the answer gives us 12. And if you look at what PyTorch have done, PyTorch already you know, outputs 12. So what PyTorch is doing is that PyTorch already, so the framework, the library, it has been, you know, built in such a way that it can calculate the gradient of all your weight, all your model weight. And if we do the same thing for the LDX2, we are going to get 8. You can try it out. Maybe I just give it to you as an assignment, because already I've written a model here. So think about this: when we are building neural networks, you don't want to, you know, you don't want to add code this, you know, gradient things. And I mean, it's straightforward to really understand that what this result you see here, this 12 you see here, is just this computation, and it's straightforward. You know, it just applies this chain rule. And imagine you have deep neural networks, and you see that this gradient would be moving from layers to layer, chain, kind of backward thing. So it starts from here, backward, it goes backward until you get to all the weight of all the hidden layers, all the layers. It's going to perform this operation, and there'll be update. And as you can see, you can view, so the gradient here is the 12. So this is what we are going to nudge, you know, x1. We're also going to nudge x2 with 8. Now, remember this formula, the weight update, right? This already we have calculated. This dl dw1. In this case, it's just like dl dx1. And, you know, we just perform the update. So we have our learning rate, 0.5. I've written a function here that would help us to, you know, calculate the new weight from the old weight, right? And now what I will just do is that, because I just need the gradient from, you know, this from this you know, calculation here. PyTorch have done that for us. So this gradient, you can access it by using the x1.grad. So if you're working with weight, you know, it is just the weight.grad. You get the gradient on this weight. And what you can do is you put the old weight here, which is your x1, which is what we started with, 2. right? And then we put the new, I mean, not the new weight rather, but the gradient of the weight, of the computed weight. And when we do that, we see that we have -4 and -1. So this -12, we multiply it by the learning rate of 0.5, right? So 0.5 times 12 is 6. Now the old weight already was what? 2. So 2 minus 6 would be -4 for x1. For x2, as you can, oh, I think I should have just written x, no, x2 new, x1 new. Okay, x1 new, because you know, we want to just update, yeah, not y1. We are just updating the weight. Yes. So as you can see now, we have -4. So this -4 just comes as a result of applying the gradient weight update formula on the computed gradient of 12. For x1, we do the operation and get -4. For x2, you know, 8. 8 times here, 8 times 0.5 is what? 4. And remember, our x2 was 3. 3 minus 4 is -1 here. So, I mean, this is basically what you do, and that is basically what we have been doing. You know, you have this forward pass, you get the loss, you do a back propagation, right? You do the weight update, and you repeat the same process, iteration, right? And now let's get more creative. You know, let's build neural network. Now we don't want to work with, you know, X, or we want to work with real weight, like what you see here. Now, let us quickly run this because we, you know, we want to, you can also set a seed so that you can reproduce the same result. And now, from what already we have done before, we have our X. X is now our input. So think about X as the input to our model, just like our feature, right? And we have the weight. You know, the weight is, you know, some weight parameters. And we have the bias, what we did in linear regression, if you remember, because we have these 2 by 3, 2 features, you know, each feature we would have its own weight, right? And there we have, you know, 2, we have just, you know, a kind of, you know, row vector, right? You know, 1 by 2. And if you multiply this, I mean, if you run this, you have the shape, you have your input, that is the shapes. I'm just defining the shapes. You have your weight and you have your bias. Now, let us perform the y-hat operation. Remember, the y-hat operation is just the linear operation, is what we know already. And why I decided to follow this is because the inbuilt the PyTorch, there is, you know, this in the neural network module in PyTorch, we have the NN.linear, you know, where it performs this linear operation. This is how it performs the operation. X times the transpose of the weight plus B, the bias. And now the weight here is 1 by 2, as you can see. The input is also 1 by 2. But remember, I told you, if you want to multiply 2 metrics, that the dimension has to be in such that the second dimension of the first matrix and the first dimension of the second matrix have to be the same. Otherwise, it would fail, you know, unless you probably carry out a, you know, element-wise matrix multiplication, then it's fine. Otherwise, now we want to find the dot product, which is always what we want to do. You understand? We want to calculate, you know, kind of, you know, optionality. You know, want to know how, you know, how much, you know, the x is orthogonal to, you know, to the weight. And so this art here is, you know, is a dot product also in Python. You can use the art. You can also use touch dot, I think dot or something. You can also take the dot product. Now, when you do weight dot transpose, what you get here is that 1 by 2 automatically becomes 1 by 2 turns to 2 by 1. You know, it kind of, how can I say, you know, it permutates it, like, you know, transpose it. Yeah, transpose it. And 1 by 2 times 2 by 1 will just give you 1 by 1. And that is what you see here you find out that the output of your model is just, you know, a 1-by-1 tensor, where 1 here can, I think in this case, represent the examples, and the other 1 here represents the output. So in a case where, let's say we have more than 1 example or something like this, let's add 5-by-4. And then you find out that the result here would be 2-by-1, because now we have 2 examples, right? We have 2 examples here, sorry, 2 examples. And if you run this, we would have 2-by-1, because now, you know, we have 2 examples and the columns are just the outputs. Now let's print out the graph of this, what we have just created. So this computational graph we're talking about. So these are the weights, these are the bias, and this is the y-hat. But take a look at this second graph here. Now, it's also what I've explained. We have the weight. Remember, it's 1/2. It's a row vector. And you have this grad because by default, I've defined it such that our weight would require gradient update already, right? Also the bias. We want to update the weight and bias. Now, this permute is just because of this transpose here, W.T. So what it's saying is that because anything you do, any operation you do, it will be recorded in the computational graph. And this computational graph is kind of abstract, right? And what it's saying is that, okay, of course, in the backward pass, I recognize that there was a permutation done, that is this transpose, on this weight matrix. And as you can see, it's not on the bias because we only transpose the weight. Now, MM backward. MM backward means matrix multiplication. And the matrix multiplication is just because of this operation here that we highlight. Because remember, we carried out a dot product, that is a matrix multiplication between the input X and the weight, and it is just automatically stored here in the graph. At this point, the bias have not even been touched, so it's just there. And now, when we carry out this operation, that is, we take the result from this, we sum it with the bias, we see this add, right? Backward. And the output y-hat is this. It's just as simple as that. This is basically what you would always find in computational graphs, right? You have this weight, all the operations are being stored in this graph, and it keeps track of what to update. In this case now, if we do the forward and backward pass, it has to update the weight. And that is what I've just done here. So here, I assume that the ground truth, that is the exact prediction, is 2. Remember, we calculate our loss, right? And we do the loss dot backward. You know what the loss dot backward will do? It will calculate the gradient of the weight. In this case, you know, we have 2 weights, right? It will calculate the loss, the gradient of the 2 weights and on the bias. And that is what you see here. When we do the loss dot backward, immediately we can print out the weight gradient and the bias gradient. When we do this, oh, okay, I think, yes, because now, you know, remember I started the example with just 1 example, if you notice, but I added 1 more example. What it means is that I have to update, you know, I have to update my, yes, I have to update this because now I have 2 examples. So let's say we have the second one should be 4. Okay, I've run it twice. Okay, we have our y-hat. Okay, yeah, we have yeah, 1/2, not 2/1. Okay, yeah. As I say, grad can created only grad can be implicitly created only for scalar output. Okay. Okay, let me rerun the whole thing. Okay, and let us print our shape 2/1. And here we would expect also Yeah, sorry. I have to ensure that it's, yeah, so I don't want to waste much time on this, but yeah, just to be clear. This would, okay, sorry. Okay, and yeah, this is supposed to work. Y minus y at. Okay. It doesn't calculate the backward y. Okay. Yeah, here we have our result. Shape 2x1. Here we have our graph 2x1. Okay, so I think I have to plus the backwards. Yeah, Rod can it's for scalar outputs. Okay, let me stick to first. Okay, let me stick to one of the examples. Okay, yeah, I think I can just stick to one of the examples. Okay, now everything is messed up. Tensor 1x2, 1x2, 2x1. Oh, expected scalar. It's quite tricky. Okay. Yeah, just give me some time. Yeah, wait. Okay. Yeah, I think I made a mistake here. So I should specify the type, or rather, I think I should just use the tensor. Okay. Yeah, I think I see where the error is now. Yeah. So yeah, sorry. So now I think it should work. So I'll just stick to one example. Yeah, I don't want to take much of my time. Yeah, so what it does, so here is we see the gradient, the weight gradient, and here we see the bias gradient, right? So which is what we would expect. We want the gradient, we want the weight. So because we have two weights, and we have one bias, right? So then we do the update as usual, right? And here we just want to repeat the process. So what we just see here is a kind of, we just, I mean, this is our y-hat, we calculate the loss. So here we just want to assume that, yeah, we still want to work with one example. We calculate the gradient. Yeah, in this case, we use main if we, okay, I think that was, I think the mistake I made here was I didn't calculate this, I think mean dot backward. So normally when you take, this loss, this formula, it outputs, when you take this loss, so it gives you the output in, so for example, if you have two examples, yeah, if you have two, you want to predict two examples, of course, you would have, two losses, right? Two losses, because you have the first loss or the first example from the formula here. You have yi minus yi. So each of the yi's represent the examples. So and here you have to take the mean, and to take the mean, of course, you have to sum and you have to average. So then you can now take the backward. You can now take the gradient. So that was why you see it was throwing an error here, because it says we can only take the backward pass on a scalar. And here, when this operation was carried out, it was not a scalar. It was two-dimensional. It was 2 by 1. We have 2 losses. So what we would have done here is to take the mean, right? And, take the backward. Unfortunately, I was not able to see that in time. Yeah. So, but now you see, we can implement this here in case we add maybe one more examples there. But let's run this. Let's see. And as you can see, we find the model update. The first loss is 19. Then the loss begins to decrease. And eventually you find your y equals 2. And, the predictions is able to get the prediction correct. Because already we have defined our, we have defined in such a way that our original label should, our y, it should output 2. And what our model is doing, our model is adjusting this weight and bias such that our, everything at the end of the day, we have to get 2 as the output. So at each run, it tries to get closer to 2. Already we have our input 2 and 3. So what it means is that these are the weight. This is the weight. These are the weight. We have 2 weights. And these are the bias. This is the bias because it's 1. And if you want to confirm, we can print out the weight already we have. And we can print out the bias. And what you do is, if this is your model, this is what your model always wants to predict. It predicts this weight and the bias. And so when we want to check, if you run through, you will get 2. And before we started the model, we just know that the output has to be 2. We want to train the model to be able to predict 2, as you can see here, the ground truth. And the model has eventually learned that. So what the model has done is that the model has now adjusted this weight, W1 and W2, and the bias such that if I put the input 2 and 3, I want to get 2. So this is the input 2 and 3 here. And because we have trained the model by adjusting the loss to meet with the, to get so close to the ground truth. And that is why you see after like 450 iteration, you see that the output is just 2. Now, let us now create a simple neural network. All along, we have just been, doing just this linear operation on one neural network, right? Now, let us create this neural network. And these are the activation functions I was talking about. So within this, for every output of a neuron, you have to pass it through, and they are specialized activation functions. You have to know when and when to, to use, activation functions. So the most popular one, and the one we are going to be using, is this ReLU. So here, it's called a rectifier linear unit. And we also have leaky ReLU. So what this means is that think about this Z as the linear operation, that is the dot product, and in addition to the bias, we are going to feed it into this function, and it takes the marks of 0 and Z. So if somehow our output is negative, ReLU will just, ReLU will not activate that neuron. It's going to kill it. So what it means is that it takes the marks between 0 and Z. And as you can see, the marks, if Z is negative, it takes 0. But if Z is positive, it takes Z. So what it means is that if the linear operation is positive, ReLU would activate that neuron. That is what I was explaining previously about activation. But if Z is negative, ReLU would kill that neuron. It will not be activated. It won't fire. And also we have tanh. You see, it maps between -1 and 1. So this maps between 0 and, yeah. So within the networks, we have to, by tomorrow when we start working with the project, then I would actually talk more about, but I think for today, we'll talk about ReLU and softmax. Last time we talked about sigmoid. Remember sigmoid when we want to, map this real value between 0 and 1. Softmax is also, sigmoid is a specialized case of softmax. Sigmoid is only, if you just want to output just one case of working with binary problems, you know, and you want just one node for the output, and you can use sigmoid. But there are cases where you have more than one class, you know, then you can't use sigmoid. You have to use softmax. Okay, let's quickly start, and so that without wasting much time, we use the same data set we used the last time, breast cancer. I'm not going to talk about it because we are familiar with the data set. So we want to build a neural network. Already we know all of this, right? We want to you know, we want to check, we want to predict if a patient have this malignant or benign cancer. But from what I see, I think the index 0 is for malignant and the index 1 is for benign. But it doesn't matter. The interpretation, you have to just understand. So now we have done all of this the last time. Remember, you know, we create our data set, we split it into train and test because we want to see the performance on the test set. We standardize. Remember, to standardize, we have to normalize because, you know, these data points are not scaled. You know, from what I explained last week, you see, we want to scale it, we want to center it, and we use the standard scaler so we fit, because now be careful about this. We are not scaling the Y and the output because it's a classification problem, right? We want to just, you know, predict like the class is 0 or 1. Unlike, you know, in regression where we can scale the Y and we can, you know, invert it back. We can do an inverse transform back. So here we will just, you know, here, okay, let me run again so that I'm sure. Here we scale it, yes, and nothing more. We scale it we center it between 0, with mean 0 and standard deviation, sigma. And for the Y, now, because already I've converted the training, because we are working with Torch, tensor, we have to convert it to tensor, right? Remember, this is just an array. Remember, it's just an array from the default, right? So we want to convert it to tensor. Remember, I talked about how you can create tensors from array. So if this is the array, then you just call this torch.tensor. And we want to work with float 32 because it's a default, and also most times the weights are float, and they are also, you know, 32-bit. So we have to, you know, think about you know, converting this. Same also, we scale the Y, that is our label. Oh, no, we are not scaling the Y, we are just converting it also to float. And because it's a classification problem between zeros and just zeros and 1, we don't have to, you know, put this to float. We have to keep it as integers, right? And as you can see, I try to print, you see. Now let us build our neural network. Good. Now, this n.linear, what it does is it just initializes weight. And the weight is what we have always been doing manually by hand. So what we do here is it initializes this weight and it performs this operation. It's as simple as that, nothing more. It initializes the weight and the bias, and it performs this linear operation. That is what the NN.linear. And the NN is from, you know, the neural network module in PyTorch. You can import it as torch.nn, and there's also some functional thing. So now we have just initialized the input. It takes an input. The first argument is the input, and the second one is the output. Remember, our neural network, in a way, sorry, I'm moving up and down because the image is here. Now, these hidden layers, because we have our input, we have another linear, you know, layer here. So we have to specify the output layer. So the output layer here is the number of hidden layer. If we change the output layer to 1, then we are just in the case of linear regression problem because we don't have multiple layers. It's just one input, then straight to output, right? But now, because we want to create a neural network, right? So we want to create a neural network. We don't want to just put 1 here. And, you know, I don't have to explicitly, you know, yeah, we can. So the hidden layer is 8. Then we have the second hidden layer. Of course, this 8 here has to be the starting point of 8. Because if you look at the neural network, like I explained initially, so, okay, in my slide, I think yeah, in my slide, if you see, I try to explain that, sorry, I have to go back to explain this. Now, think about this hidden layer as that 8. 1, 2, 3, 4, 5, 6, 7. This is 7. Now, these layers would serve as input to these next layers. So these layers have to, to serve as input. So we have to ensure that the number of layers here must correspond to, the number of weights we are going to initialize in the second layer. And that is why this 8 has to be the same with this 8. Then we can also define another, let's say 4. We don't have to use 8. So we define, so now we have another hidden layer. That is, and the hidden layer, it takes 8, which is the end of the first layer. Then we have 4 hidden layer. Then the last layer would be 4 times, like the last layer would just be the number of classes. So what we would have, our neural network would be like this: the input X, then it's going to have, 8 hidden layers. So think about the neuron stacked 8. Then the next one would be 4, which I defined here. So this 8 here is just, the 8 here is just ensuring that we are sure to initialize the weight, it has to be the same. The ending of one layer has to be the beginning of another layer. And the next one would be 1, because this, 2, because the number of classes, we have 2 classes here, right? We want to predict benign and malignant tumor. So this is how our network architecture will be. We have the input, we have the first hidden layer, 8 neurons, which is here. We have the second hidden layer, which is 4 here. And we have the fourth, the output, which is not a hidden layer, just the output, which is the number of classes. I didn't explicitly put 1 or 2, but depends, if you want to build a general network that can accommodate any number of class, then it's better you just, yeah. So here is just the ReLU. So we, of course, the forward method here ensures that when we call this model, it returns this, it performs this operation. So for the linear layer, because our X is our input model, right? Is the input. So it performs this linear operation on the input, right? And it, the ReLU activation function, we decide if it's going to activate or not. We perform also the second one, and the third one, and that would just be the end. So now let us instantiate our model and let us see what is going on. So we have our input. Our input is gotten from our shape, which is, in this case, I think 30, if you remember the last time, where we talked about where we used the, it has to be 30 or 28 or something. Okay, it's 30, so that would be the input. So the input size here will be 30. All right, and let us build the computational graph. How does it look like? So it looks like this. Okay, now to be very fast, because I've built this network, it's just exactly what we have been doing. It's just some, series of linear layers stacked, and as you can see, it performs this operation. So we define our loss, we define the cross entropy. I will talk about that tomorrow in detail. And we kind of, optimize. We also introduce a kind of optimization method, which helps to, to guide the model to, using a kind of momentum to push the gradient to its global minimum. So that is what we do here. And remember, we have to activate if we are working with CUDA. CUDA is, it also runs on the GPU. So you can decide if you want to run on CPU or GPU. So we just run the same algorithm. Remember, we have the, we set the optimizer to 0. We have the predict, we predict. We call the model because already we have defined the model here. Here, yes, we define the model here. So when you call the model, it's going to just run this method and it's going to output X. And also we have to be sure that this criterion, that is this cross entropy loss, it performs the softmax, because remember the output here, the output are just logits. They are numbers between -infinity and infinity. Tomorrow I'll talk about that also. So when we run the model, it trains, as you can see, we get this. And now let us try to predict. I'll send you the Python script. And remember the last time we did this same problem, someone asked, can our model perform better? I said, well, I don't know. Depends on how well you're able to, how well you're able to continue training. And at some point, we saw that when we even increased the number of iteration to about 50,000, we still had, one misclassified. But now look at, in this our neural network, the model has been able to move this particular one correctly, and we just have this. So in essence, we just solved the same problem using different architecture. The first one was a simple linear regression problem, was just a simple linear regression. As you can see, just one neuron. You just think about this as just one neuron with the activation function, just the output probability. Now think about this as an artificial neural network. And as you can see, it is stacked. So we have one layer, we have another layer, and we have one last layer. Now we have two hidden layers, that is 8 and 4. And the output is 2. The output, it outputs probability distribution. So as you can see, it performs better, clearly, because if you want to think about classification, this simple linear logistic regression misclassified this example and this. But the neural network, the artificial neural network we constructed, we have 8 hidden layers and 4 hidden layers. It's able, in a way, try to correct that. And that shows how powerful this method can be. It helps a lot to, gives a more complex, representation of the problem. It helps to learn, complex, patterns. And then it means that the model is able to predict correctly all, benign tumor. As you can see, 42 correctly predicted. But the malignant tumor, unfortunately, misclassified 1, which is fair compared to the last one. And if we plot the ROC curve, we see that it's 99%. Here, the last time we plot the ROC, it was 98. Just that extra 1 has made it improved. And here we have the, just to visualize the activation function. But I will talk about this in the next slide. It doesn't really matter. I just wrote this code just to show us how these activation functions looks like. The ReLU, this is the derivative. Also, this is the exponential linear unit. We also have the switch function, also works like with the sigmoid. And I will stop for today. And yeah, probably at least in this class, I've shown that we can construct a simple neural network, something like in this form, but in this case, we just did 2 hidden layers. Tomorrow, we are going to do a project. It's going to be interesting. We'll build an artificial neural network that can help to classify handwritten digits. And also, we would use CNN on this same problem, and we would compare if convolutional neural networks can indeed, be better for images, like grid-like data like images. Yeah, thank you. And I'm sorry we're about 4 or 5 minutes late, which is also expected because at the start we have to wait also for about 5 minutes. So if you have questions, I'm open. And if you still don't understand, I will still send some links in my slide. And yeah, so that we can also practice more. Thanks a lot, and see you tomorrow. If you have questions, you can put in the group chat. Yeah, thanks a lot. Okay, thank you.
Hello.
And see you tomorrow, same time.
Augustine.
And I promise you would
Hello.
like the project tomorrow.
Hello, Augustine.
Thank you too.
Hello.
Thank you.
Hello.
Thanks to everyone. I have to leave for another meeting now, and so I have to.
Hello, Augustine.
Hello, doctor.
To stop this section.
Hello, doctor.
Hello.